I am Jun Ho at Siemens EDA. We have been developing EDA methodology for assessing chip package interaction effects on IC chip performance and reliability. Today, I will present a tool calibration methodology by employing die warpage measurements. These schematics illustrate the problems that are related with package assembly. We employ clean chip design and complete fab process to produce dies. On a die level, the chip performance looks good. Then after assembly that accompanies high temperature process, the degradation in chip performance may be detected. Here, chip package interaction or CPI is defined as an interaction between package-induced stresses and semiconductor devices. In eCPI, deformation of silicon results in carrier mobility change. For strain engineering, simple empirical piezo-resistance relations can represent mobility shift due to mechanical stress. In MCPI, highly stressed regions are prone to interconnect fracture, cracking of ultra-low K dielectrics, or interconnect lamination. For non-stressed state, the failure criteria such as von Mises stress and maximum principal stress can be calculated. Now we present EDA tool flow for analyzing CPI-induced problems. The methodology of effective material properties, EMP, is an efficient way of representing different material components that are present in a design layout without constructing actual geometrical objects. Following the theory of anisotropy composite material, the methodology considers that each interconnect layer consists of parallel metal fibers embedded in an insulator matrix. So for each layer and each square bin, the tool obtains anisotropic effective properties. The EMP methodology has been validated successfully against the traditional sharp boundary geometrical model for thermal stress analysis on a small layout area. We see very good match between these two methodologies. The tool performs the multi-scale analysis from package to layout feature scale that ranges from centimeter to nanometer. With the multi-scale simulations approach, the stress variations due to die warpage, edge and corner effects, and bump interaction are obtained. On the other hand, the nanometer scale stress variations are generated by local feature scale variations in mechanical properties. These are obtained from detailed simulations of small region of interest. So the link between the package scale and detailed simulations is provided by boundary conditions. These are some of the results that come from two-step multi-scale simulations. These left figures show the results of multi-scale stress simulations for obtaining bending-induced stresses. Global die scale results is shown, and the subsequent sub-modeling has been performed with final grid size on a selected IP block. The right side figures compare the distributions of thermal stress components inside an IP block obtained from global and submodeling. The 1D stress profiles for both cases show that the global scale modeling only can miss small scale variation and can lead to inaccurate prediction of device characteristics. Now we present mechanical CPI analysis, MCPI analysis. For MCPI analysis, the tool calibration on the electrical measurements may not be available as it is performed at pre-design stage during process development. Here, a possibility to perform the tool calibration against warpage of a package and a die is demonstrated. We use the experimental measurement on Intact 3D package. The Intact is designed with a chiplet-based 3D technology and consists of 6 identical chiplets, active interposer, and with TSV and PCB. The altitude measurements are collected during heating and subsequent cooling to room temperature. The measurements are done by Altiserve 520. We start with standalone PCB. The PCB is modeled as 3-block structure. For each block, tool extracts uniform smeared effective properties, or EMP. The properties of PCB are further refined by calibrating against warpage measurements. The figure A summarizes a measured warpage value delta Z that is defined as the height difference between center and edge locations along the 2 diagonal directions. During heating up to 150 degrees C and then subsequent cooling for both directions, delta Z profiles are similar during heating and cooling. So this allows us to collect all the data points for each temperature and obtain linear regression curve fit for measurements. The resulting linear curve is shown in B together with error bars. The figure also demonstrates the good fit between measurements and simulation results after adjusting parameters. For chiplet-only sample, the warpage measurements were made on BOL top surface. Here, the tool extracts uniform smeared properties for BOL, and these properties are further calibrated. As you see, a good fit between simulated versus measured was obtained. After tool calibration, we obtained the simulation results on chiplet BOL surface at 2 different temperatures. In 1D profile along a diagonal direction, the simulated and measured results are compared. The central region show micro bump, microscale peaks corresponding to copper pillars that are exposed to air. The results for 350 degrees C exhibits convex surface as opposed to concave at 150 degrees C. The transition in warpage profile and overall map pattern matches reasonably well with measurements. Rated parameters are now employed to simulate the surface profile on a full stack package at room temperature by taking highest uniform die attached temperature of 230 degrees C. The warpage at room temperature is simulated. We compare our simulated top surface 1D profile along horizontal and vertical cut lines, both along the horizontal cut line in A and vertical cut line in B. The simulation curves agree well within the measurement error. And we also compared many different effects, but none of these were the major impact on the surface profile. tool can analyze now non-uniform temperature and the resulting stress during chip operation conditions. In this simple work, we placed one dynamic, three static power source on the die corners. The tool can keep track of time evolution of temperature and the resulting thermomechanical stress. The right column maps show the change in die warpage as time increases. The stresses can be damaging, especially in the case of transient temperature, because low frequency oscillations of deformation or stress can cause fatigue of interconnect components. In conclusion, we presented our multi-scale simulation methodology for analyzing CPI stresses. For mechanical failure analysis, we demonstrate that the workpage measurements can be used for the tool's calibration. We also presented the tool's capability of analyzing CPI stress-induced reliability issues under chip operation condition when the link between thermal and mechanical simulations are provided. Thank you.